Hi students, small request Nana. Without subscribing my channel, you are watching my videos. Please subscribe my channel students. Please support me. Then I can do more videos students. Please Nana, please. Thank you students. In today's session, I am going to discuss about the VBT valence bond theory. It is the topic from the 12th class coordination compounds lesson. Here I am giving the two best trick students, trick box 1, trick box 2. Okay, before only I wrote these two to save the time. Okay, first I'm going to discuss the complex Nana. So simultaneously I will discuss these trick boxes students. Okay Nama. So first complex is CONH3 3 plus. See here this complex. See, this is the central metal atom, it is the ligand. So central metal atom, we know that metals always ready to lose electrons. Because of loss of electrons they become electron deficient. So that's why they are ready to accept the electron students. Ammonia is ready to donate the pair of electrons to the central metal atom because ammonia is the ligand. What is the ligand? It is ready to donate the lone pair of electrons to the central metal atom. So it is the ligand, it is a central metal atom. Now I'm going to take the first central metal atom, cobalt. So first I'm going to calculate oxidation number of the central metal atom from this complex ion. See here, first trick box 2. In trick box 2, first what I told you, calculate oxidation number of the central metal atom. Trick box 2. What is the trick box 2 students? Calculate oxidation number of the central metal atom. And B, what is the trick box to B students? Identify ligand. So the given ligand, whether it is a strong field ligand or weak field ligand. Are you clear? So you have to identify the ligand students. The given ligand is strong field ligand or weak field ligand. Okay, strong field ligand examples NH3Cn minus students. These two are strong field ligands. Fluoride and chloride, these two are weak field ligands. If suppose in the given complex strong field ligands are there, 3D it can pair up the 3D electrons. Nana. If it is weak field ligand in the given complex there, then 3D electrons it cannot pair up. Are you clear? Strong field ligand, in the case of strong field ligand, 3D electrons pair up. In case of weak field ligand, 3D electrons do not pair up. What is this 3D electrons? That I will discuss you later. Okay, so first calculate the oxidation number. Now I am going to calculate the oxidation number of the central metal atom, and after that the given ligand is strong field ligand or weak field ligand. Now we have to check. Okay, see students here. So this is the complex compound ion. We have to find first of all oxidation number of the central metal atom, cobalt. So I am going to calculate cobalt. I have to find it. So I am taking cobalt as X plus 6 ammonia ligands are there. NH3 is a neutral ligand students. It is a neutral ligand. Oxidation number is equal to 0. And charge here, how much given? Plus 3 given. Okay. Then X is equal to how much students? 3. Here 6 zeros are 0. X is equal to plus 3. This is the oxidation number of cobalt, Nana. Are you clear? Oxidation number of cobalt. Okay. This is the first in rule 1. A bit is completed. That means oxidation number, calculate the oxidation number of the central atom completed. Now what is the second B bit students? Identify the ligand. The given ligand is strong field ligand or weak field ligand. Now see, I told you examples: strong field ligand NH3Cn minus, weak field ligand F minus and Cl minus. So NH3 is which ligand students? NH3 is a strong ligand. Are you clear? See here. So NH3 is which ligand students? NH3 is strong field ligand. Are you clear? It is a strong field ligand. Okay Nama, it is a strong field ligand. So that's why it can pair up 3D electrons students. It can pair up the 3D electrons. That only I told you. Now if it is strong field ligand, 3D electrons pair up. Yes or not? 3D electrons pair up. Okay, this is about strong ligand. Okay, strong field ligand. Now see students here, oxidation number plus 3. Now I am taking the oxidation number of I am taking the atomic number of central metal atom. See here, cobalt atomic number how much, Nana? 27. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt 27. So what is electronic configuration? Argon, 4s2 till here 20 completed, 3d7. Okay, so this is electronic configuration of cobalt, but here how many electrons lost, Nana? 3 electrons lost. So that's why CO plus 3. That means 3 lost electrons. So from the valence shell, 2 electrons lost, 1 more electron from 3D it is losing. So that's why its electronic configuration is here 1 electron lost, here 2 electrons completely lost, 3d6, 4s0. Correct? This is electronic configuration 3d6 4s0. Okay, now orbitals, electronic orbital structures I'm taking 3d6 4s0. 3d is nothing but how many orbitals will be there in 3d subshell. See here, I'm taking first 3d. In 3D, total 5 orbitals will be there. 1, 2, 3, 4. This is 3D, students. And 4s. In 4s, how many? 0. No electrons. No? So in 3D, total 6 electrons are there. 1. How many electrons? 6 electrons. 1, 2, 3, 4, 5, 6 electrons are there. 4s is completely vacant. Now you see, students, the given ligand is strong ligand or weak field ligand. Yes, NH3 is strong field ligand and it can pair up the 3d electrons. It is a strong ligand. Okay, so here 6 ligands are there. Each ligand is donating 1 pair of electrons. 6 ligands are donating 6 pairs of electrons to the central metal atom. It can form the 6 coordinate covalent bonds with the central metal atom. That's why its coordination number is 6. Are you understanding? So here NH3, in NH3 nitrogen is a donor atom. It can form the 1 coordinate covalent bond with the central metal atom. Total 6 ammonia ligands are there. It can form the 6 bonds with the 6 bonds with the cobalt atom. Are you clear? So here it is a strong ligand. So here how many ligands are there? Total 6 ligands are there. That's why 6 ligands are donating the 6 pairs of electrons to the central metal atom. So in central metal atom, how many orbitals required? 6 vacant orbitals required, because 6 ligands donating the 6 pairs of electrons to the central metal atom. That's why in cobalt, total 6 vacant orbitals required. So that's why here in 4s, here only 1 orbital is there, but it is a strong field ligand. It can pair up the 3d electrons. So here already paired. These are unpaired electrons. So first of all, these electrons will get paired. So I am taking here, this is CO plus 3. This is 3d. So what I told you here, it is already paired. First take 5 boxes, 5 orbitals in 3D. Already it is paired. Remaining electrons will get pair up. Correct? Because it is a strong field ligand. Are you understanding? It is a strong field ligand. It can pair up 3D electrons. So 3D electrons already it is paired. Remaining 4 electrons will get paired here. These 2 here, these 2 here. Then here in 3D we will get the 2 vacant orbitals, so vacant boxes, and here 4s is completely vacant. See here how many ligands are there, students? In the given complex compound, 6 ligands are there. That means in cobalt 6 vacant orbitals required. But here how many are there? 1, 2, 3. 1, 2, 3. Only 3 are there. Still 3 boxes required now. So that's why I am taking 3 boxes from 4p. Okay, it is completely vacant. It is present in the valence shell, 4th shell. Yes, now. So 4p I am taking. Total how many vacant orbitals there? 1, 2, 3, 4, 5, 6. Correct? So 6 vacant orbitals are there in cobalt ion. So it is ready to accept the 6 pairs of electrons from the 6 ligands, students. Okay, now these 3d orbitals, 4s and 4p orbitals undergoing hybridization. See here how many orbitals? 2d orbitals. 1, 2, 2d orbitals. Next 1, which orbital? S orbital. Next how many p orbitals? 3 p orbitals. 3 p orbitals. Clear? So 2 d orbitals, 1 s orbital, 3 p orbitals. Undergoing hybridization, students. Undergoing hybridization. Then produces total how many students? 1, 2, 3, 4, 5, 6. 6. D how many? 1, 2. D how many? 2. D2. S how many? 1. P how many? 3. D2 sp3 hybrid orbitals. Clear? D2 sp3 hybrid orbitals are formed. Okay, so now this D2 sp3 hybrid orbitals I am taking here. See, Nana. D2 sp3 CO plus 3 D3, this is 3D. This 3D here 3 boxes you keep separately. These 6 boxes you write in one place. See here, the first I am taking 3D, 3 boxes like this. And here 1, 2, 3, 4, 5, 6. The 6 sp3 D2 hybrid D2 sp3 hybrid orbitals formed, that you have to write in one place. 1, 2, 3, 4, 5, 6. Okay, so this is which one, students? This is 3D. This which one? 6 D2 sp3 hybrid orbitals. Clear? Hybrid orbitals. Orbitals are formed. Now 3D, how many electrons are there? 3 paired kada. So take that 3 paired electrons as it is. These 3 I am taking separately here. And remaining 6 orbitals, so here I am taking, these are D2 sp3 hybrid orbitals. Are you understanding? Right. Now these 6 D2 sp3, this is D2 sp3, D2 sp3, D2 sp3, D2 sp3, like this 6 anamata. Okay, 6 D2 sp3 hybrid orbitals. Now these 6 D2 sp3 hybrid orbitals of the central metal atom cobalt undergoing overlapping with the how many ligands, students? 6 ammonia ligands filled orbitals. Okay now, so these hybrid orbitals, okay, 6 D2 sp3 hybrid orbitals undergoing overlapping, okay, with the which one, students? With the filled orbitals of 6 ammonia ligands. Filled orbitals of 6 ammonia ligands. Are you clear? 6 ammonia ligands. So here overlapping. So here this is undergoing, these hybrid orbitals are undergoing overlapping with the filled orbitals of 6 ammonia ligands. Here the same atom orbitals are undergoing hybridization. Are you clear? Here hybridization, here overlapping. Right. Now whenever undergoing overlapping, students, cobalt ion and 6 ammonia ligands, what is happening, students? The 6 ammonia ligands donating the 6 pairs of electrons to the central metal atom. Total central metal atom is having the 6 vacant orbitals. Now 6 ammonias are donating the 6 pairs of electrons. See here, orbital structure. This is 3D, completely paired. Here 6 boxes, 1, 2, 3, 4, 5, 6. Okay, these are 6 sp3d2 hybrid orbitals. Now these are undergoing overlapping with the 6 ammonia ligand, students, filled orbitals. Now these are electrons of ligands. See here, 6 hybrid orbitals filled with 6 pairs of electrons, students. These electrons from 6 ammonia ligands. Are you understanding? So these electrons of ligands. Electrons of ligands. Right, I'm taking here these 3 electrons pairs as usual, 3D, and here these electrons of ligands. So that means here 6 ammonia ligands are donating the 6 pairs. Now here 1, 2, 3, 4, 5, 6. Clear? 6 pairs. That means 6 ammonia ligands donating 6 pairs of electrons to the central metal atom. 1, 2, 3, 4, 5, 6, 6 pairs. Okay, now 6 pairs. Now we have to write the hybridization geometry, magnetic property. Nana. So first here conclusion. What is the conclusions you have to write here? First one, hybridization. Tell me students, what is hybridization here? Which hybridization? D2sp3, correct? D2sp3 hybridization. This is the hybridization. Okay, so right here D2sp3 hybridization. Next one, geometry. Geometry. What is the geometry? D2sp3 hybridization. In trick box 1, I told you D2sp3 hybridization here there. D2sp3, what is the geometry students? Octahedral geometry. You have to remember these shapes, Nana. D2sp3k means octahedral. Okay, so octahedral complex. So the given complex is which complex, Nana? Octahedral complex. Geometry is octahedral. Next one, magnetic property. What is the magnetic property? The given complex is diamagnetic or paramagnetic. Now see students, here you have to see only 3D. 3D electrons are paired, unpaired, all are paired kada. 3D electrons paired means diamagnetic. Paired means diamagnetic. Clear? Diamagnetic in nature. Okay, all are paired, diamagnetic in nature. So this is about the magnetic property students, because here why it is diamagnetic? Due to the absence of unpaired electrons. All are paired kada. Paired is nothing but diamagnetic. Paired means you have to remember this one. Paired means dia. Unpaired electrons there means what we will call para. Okay, it is paramagnetic. Understood, Amma? This is the magnetic property. Now it is a low spin complex or high spin complex. Now we have to see. So what is the high spin complex, students? The number of unpaired electrons in free metal ion and complex is same. The number of unpaired electrons in complex ion. In complex and free metal ion. So here see, free metal ion, how many unpaired electrons are there? 1, 2, 3, 4 are there. Free metal ion. How many are there? 4 unpaired electrons are there. Okay, now in the complex, how many are there, students? It is the free metal ion. In the complex, how many are there unpaired electrons? Is there any how many is there any unpaired electrons? No, all are paired. That means here unpaired electrons are different in the case of free metal ion and complex. Are you understanding? In the case of free metal ion and the complex, number of unpaired electrons are different. So that's it is a low spin complex. Which complex? Low spin complex, because the number of electrons are unpaired electrons different, Nana. Where different, students? In the free metal ion and the complex. Understanding? So in the complex, Nana, here there is no unpaired electrons, all are paired, but here in the free metal ion 4 unpaired electrons are there. So that's why number of unpaired electrons are different in case of free metal ion and in the complex. So that's it is a low spin complex, students. It is outer orbital or outer d orbital complex or inner d orbital complex. How to tell? Students? Outer d orbital, inner d orbital. See here in the hybridization, first which one came, Nana? D orbitals came. In the hybridization, first d orbitals came. Okay, so first d orbitals came means 3d orbitals, because here I told you 3d orbitals. Here 3d vacant orbitals are undergoing hybridization. That means 3d is nothing but it is inner d orbital. Inner shell ka the third shell, fourth shell is the valence shell. But here which shell d orbitals are involved in the hybridization? 3d. The only d you have to see. 3D orbitals only involved in the hybridization. So that's why it is inner d orbital complex. If suppose 4D, here after 4p d orbitals also involved in the hybridization, then that is outer d orbital complex. Are you understanding? Here only inner d orbitals involved. Are you understanding? So that's it is inner d orbital complexes. Inner d orbital complex. So the given complex is inner d orbital complex. Okay, inner d orbital complex. These are the conclusions, students, from this VBT. See here, first we have to calculate from the tick box 2. You have to find the oxidation number, students, of the central metal atom. Next, you have to identify the ligand is given ligand is strong field ligand or weak field ligand. Next one, if it is strong field ligand, 3d electrons pair up, nana. If it is weak field ligand, 3d electrons cannot pair up. So here take cobalt atomic number, electronic configuration, 3 electrons lost, oxidation number +3. So right here oxidation electronic configuration, this is the orbital structure. So here total how many 6 ligands are there? That means 6 vacant orbitals required in the cobalt. So that's why here 6 vacant orbitals you are taking. These orbitals are undergoing hybridization, produces 6 D2sp3 hybrid orbitals. It is a strong field ligand. So that's why here 3d electrons will get pair up like this. Okay, next one, these orbitals are undergoing overlapping with the filled orbitals of 6 ammonia ligands, students. Then 6 ammonia ligands are donating the 6 pairs of electrons, 1 2 3 4 5 6, to the central metal atom, electrons of ligands. Then conclusions, hybridization, octahedral geometry. This geometry from where we can understand, students? From the trick box 1. Are you clear? From the trick box 1 you can understand what is the geometry. So we got D2sp3 octahedral. So sp3 before different, first only d is there, that is inner orbital complex. If suppose after sp d orbitals there, means that is inner orbital complex, students. That only difference you have to remember, that one. Okay, so hybridization, geometry, octahedral, magnetic property, diamagnetic. Because if only you have to see 3D, if all paired, diamagnetic. Unpaired means paramagnetic. It is a low spin complex because in the free metal ion and the complex, number of unpaired electrons are different. Here 4 are there, here no unpaired electrons. So that's a different low spin complex. It is inner d orbital complex because in the hybridization sp3 before d orbitals there. Starting d orbitals there means that is inner d orbital complex. If suppose after sp3 d orbitals there, that is outer d orbital complex. Are you clear, students? I hope you like this video. If you like this video, please like, share, comment and subscribe my channel, students. Thank you, students.